This gets a factor of e to the minus 5, this gets a factor of e to the 5, cancels out. So it means that if you try to do this, you're not going to get infinity anyway. Because the action does not depend on the choice of scale of the matrix, so you're going to get the integral of this scale factor is infinity. So to do string theory, you actually divide also by these sort of Y transformations. These are the Y transformations. Just the scaling of the local scaling of the matrix. If you think about this, it's a very strange symmetry. Not this that the theory of free bosons in two dimensions, coupled to some metric on the surface. Well, again, the theory of free bosons in two dimensions, massless free boson, does not seem to change if you change completely your metric. So this can get a space that is flat and make it into a tube, make it into a ball, make it into a completely weird exact shape. But somehow the collection factor of the free scalar is supposed to be not affected by those transformations.
Why is the viral transformation not a subset of the dimorphisms? This is it for both free scaling and all free
bosons. Well, because I'm not touching the coordinates. Also, I'm not touching these x's. So while I do this, I leave x to x. I'm not touching those. Now, this one is actually quite convenient because, see, in one dimensions, we had 1 degree of extra freedom, and we had 1 parameterization, so we could just get rid of this new degree of freedom. But the metric in 2 dimensions has 3 components, but they only have 2 isomorphisms. So if we didn't have one symmetry, it would be left, we would not be able to sort of fix away the metric completely. We would be left with some free remaining part of the metric, which would make the action very complicated. So the metric would be something like a new degree of freedom. It's really dynamic with a very complicated action. But this is what about it. And there is a nice theory that at least locally, you can start with any metric you want, use diffeomorphisms and wild transformations to make it flat. Now globally that's not exactly true. So globally there is a little bit of extra freedom left on how you glue together these different flat patches of the metric. And we will see later it has something to do with something called the complex structure of the surface. Pretty much it has to do with the fact that you pitch your gauge so that your metric is flat. Just this. And you go to complex coordinates. So the metric becomes the z is bar. Okay. Now you can do a complex, a monomorphic change of coordinates. Your metric will become just like that. So crucially, complex coordinate transformations, homomorphic coordinate transformations, just multiply the metric by something, which means they can be eliminated by well-transformed Y transformation. So if you try to throw away as much as you can on the metric by using Y transformations and diffeomorphisms, so if you try to gauge fix everything by saying I want the metric to be flat, I can do it in some patch, I can do it in some other patch, but the different choices I make might be still related in different patches by homomorphic changes of coordinates. And to start by gluing together flat matrix with complex coordinate transformations, I can actually still make very interesting surfaces. So by if I'm given a complicated surface like this, I can patch it out from a bunch of flat pieces of flat space with some isomorphic transformations. Now for a while
Can you repeat that part? So I'm not entirely sure what the non-triviality of that is. Are you?
Suppose I give you a sphere. Okay, for some reason I want to do a integral on the sphere. Okay, this is not a sphere, but suppose for some reason I want the surface to be just a sphere. Even better, some complicated, like a pretzel. Okay. Now, there is no flat metric on the pretzel. There's no way to make the pretzel flat everywhere. For example, you know that the integral of the curvature of an whole pretzel is a constant, which is called the genus of the pretzel. And this is genus minus has genus 3. Okay. So you cannot get 3 by integrating 0. So the pretzel cannot be made flat everywhere. What they can do is to just break a pretzel in chunks, make the metric flat on each chunk of the pretzel, and then patch it up by these sort of transformations, which allow me to glue together flat pieces of flat metric in a material way. So this is a valid operation in this context because, see, the action is well defined on one patch, it's well defined on the other patch, and the action on the two patches agrees, because I'm going from a patch to the other by a diffeomorphism together with a Y transformation. So I can glue together this local calculation globally. And it makes sense, at least classically. Now, but mechanically there are different issues. Yes?
Sorry, I still don't quite get how you can make it flat by integral across the one uses in complex.
No, I'm saying, make it flat. So there is a theorem, it's a difficult theorem of analysis. That given any metric, you can make it flat with a diffeomorphism and a Y transformation. It's a theorem, I'm not going to prove it to you, I don't know how to prove it. Locally it's kind of intuitive because there are 3 degrees of freedom in the metric, there are 3 degrees of freedom to play with, but...
And what is the purpose of going from D1 to the complex coordinate?
It's just to show you that although once I make this operation, make the metric flat, I did not fix my degrees of freedom completely. So if you make the metric flat here, and I make it flat, and then we compare nodes, we might discover that we didn't make it flat the same way. But our choices of coordinates differ by homomorphic change of coordinates. Okay. Now, luckily, let me do that. So, once I make the metric flat, I can get rid of almost, I can get rid of h. So this is my action, which just becomes something very simple. Okay. So my path integral over the axis became Gaussian. So trivial, free field theory on my circuit. Same as it happened in the past. So calculations would be actually pretty straightforward. Yes.
So you're saying that the level of the action both are equivalent, right? If I measure calculations and locally my metric is flat. But if I just calculate, for example, the equation of motion, they have extra structure than for just fixing this, right?
No.
I have more constraints on
Sorry. I'm doing a gauge fixing, so I still have to pay the usual prices doing gauge fixing. So, for example, I got rid of h, but it's true. The equations of motion for h still have to be imposed. Like the Coulomb constraint in gauge theory. So, it's perfectly true I had to work with this action and at the same time also impose the s over the HAD, which is the test tensor in two dimensions, to be zero classical. So, I had to figure out how to impose this quantum mechanically. But it's no different from what you've seen in gauge theory, but you had to impose current conservation after you gauge fix. Now, the two problem is that this is all classical, and while simply, so which means that if you want to actually make things work, I better make sure that the symmetries are symmetries not just of my action, but also of my measure in the path integral. Now, it's possible to make the measure invariant under parameterizations. I told you just change the coordinates. So how do you regulate the path integral usually? Typically you expand your field in some modes, and then you truncate. You throw away all the modes beyond a certain point. And so you can throw away all the modes which have a fluctuation which is faster than something. And you can measure how fast is this fluctuation just by using the metric itself. So if you do that, there is no dependence on your condition on the actual choice of coordinates. So it's easy to define your measure in a way that is invariant under diffeomorphisms. But to do so, you use the metric. I mean, to regulate, you need some notion of distance. You need to throw away the modes which are moving too fast, have too much energy. So if you do it in a way, if you define your cutoff in a way that depends on your choice of coordinates, then you're in trouble with diffeomorphisms. That's bad. If you define your notion of cutoff by using the metric, you're fine with diffeomorphisms, but you're going to be very careful with wild transformations to change the metric. And indeed, if you regulate this in a way that is diffeomorphism invariant, it cannot be also invariant under wild transformations by itself. So if I take a free boson, it's not invariant. The measure is not invariant under wild transformations. So I have. Now, we will kind of see that this. So this is what's called usually an anomaly. I have some symmetry of my classical action, but it turns out there are troubles regulating the path integral so that the symmetry holds true. And if the symmetry doesn't hold true, then I cannot gauge it. So, typically anomalies happen for some topological reasons. So it can be rather hard to wrap your head around until you've done a few examples, because depending on how you regulate your theory, you'll see the anomaly, the problem pop up somewhere. You say, okay, I messed up. I regulate differently, and the anomaly pops up somewhere else. You can squeeze your measure in many ways, but the anomaly always pops up somewhere. So it's something topological about it. Just this, you feel like to make something like this flat. You can, but you can do it locally. So on the hand, because it's topological, so it depends on, it can be captured by relatively little information. At the end, there is just one number, which characterizes how not wild invariant the measure can be. So in the wild transformation, this measure transforms in a certain way, and the failure to be wild invariant depends on some number, which is called the central charge. Each of your coordinates in space-time contributes something to this central charge, one thing. And then the integral over the matrix contributes something else, which happens to be for minus 26. So if you put 26 coordinates in your space-time, the anomaly cancels and this makes sense. So vanilla string theory, bosonic string theory, works if you put 26 coordinates in your space-time. If you don't put them, then the wild transformations don't decouple. You try to get rid of the metric, but you're still left with the dynamics of this conformal factor. And well, you get something else from what you want to get. Instead of getting something that looks like maps from your string to space-time, you get an extra coordinate with a funny action that comes from the wild transformations. You get something that can still make sense. It's called non-critical strings, but it's not what we're going to try to discuss in the next lectures. Questions? Yes, some answer.
Yeah, so you said that we cannot simultaneously ensure diffeomorphism invariance and wild.
Actually, the full statement that you cannot ensure wild invariance, diffeomorphism symmetry, and Lorentz invariance. There are ways to squeeze things around so that it looks like you got wild invariance and diffeomorphism invariance, but because you screw up one of the coordinates of space-time or something like that. So.
Okay, so the procedure via that, we usually hold on to the rents.
Yes.
And diffeomorphism.
Well, it depends. So if you look at Polchinski, there are a bunch of different quantizations. There's something called light quantization, in which you pick two coordinates and you treat them different from the others. Essentially, you use your two diffeomorphisms to gauge fix those coordinates instead of gauge fixing the metric. And then the metric looks out by itself. All is nice and fine, there are no ghosts, nothing to worry about, except that Lorentz invariance is broken unless you have 26 dimensions. So in these lectures, I just try to do it in one way. So I keep Lorentz invariance. I'll work with some ghosts. And,
is it equivalent, like, so we've essentially got these three things that we're trying to preserve in some sense.
Yes.
So you pick any two while you're varying the so your path to quantization in terms of the three possible combinations that you have of 2 at a time.
I'm not sure I would...
The same series or the same thing?
If you're in 26 dimensions, yes. But because it's all gauge fixing, see? And there is it's possible, usually, if you do things properly with ghosts and we have the symmetry, it's possible to show that different gauge choices are equivalent. So we'll actually try to see why that happens. Now, that's used. As you hold that, typically, so gauge choices which let you end up with a free action are really preferable because it means you can actually do calculation. In principle, if you had an oracle that knows everything about two-dimensional field theory, you could make crazier gauge choices. So you get them interacting two-dimensional quantum field theory, and you could ask the oracle to solve it for you and to still do string theory. But it's nice that there are gauge choices where things are actually free to watch it. At least for flat space. In the time, if you want strings moving in flat space. If you want strings moving in other space-times, then things are not free. Then they can get what they... Okay, well, pretty much done. So, let me see.
So, showing like my head around the speech vision. So, for example, in QED, we have to what about you said, when we're trying to quantize, either we restrict my operators in my token space, or I first find the classical solutions, then I restrict my classical solutions and then quantize those. Is there an analogous thing to what you're saying here?
Classical.
So the difference between the Coulomb gauge and the Lorentz gauge.
I mean, both Lorentz gauge and Coulomb gauge have the same kind of gauge fixing that you impose some conditions to kill your gauge degrees of freedom.
Well, I agree, but in one case you restricted your open space after, like you allow wrong quantize and say, okay, this operator acting in some states is gonna...
I mean, if you want to do it properly, you use the quantization in